In this video, we'll look at the idea of optimization, which is about finding the largest and smallest values of a function on an interval. When many people buy a car, they think about its fuel economy, how far it will go on a gallon of gas. One thing that many people don't realize is that your fuel economy is affected by the speed at which you drive. In this video, we'll examine the relationship between fuel economy and speed, and try to find the speeds that will give you the best and worst fuel economy. Here is some data that was collected by the Oak Ridge National Laboratory. In 1984, they took 15 different cars, drove them around a test track at different speeds, and measured their fuel economy. So, for example, they found that when they were driving the cars at 45 miles per hour, the cars on average had a fuel economy of 33.5 miles per gallon. In this table, we can see what the largest and smallest values of fuel economy are, but the table only gives us data at specific speeds, and it's possible that cars might maximize or minimize their fuel economy at speeds that are in between those displayed in the table. To get a better sense of the patterns in our data, let's look at a graph. This graph shows the data points in the table. To get a better sense of the patterns in the data, we can add a trend line, and we can also find a formula for this trend line. This shows the equation of the function f of s, fuel economy as a function of speed, measuring fuel economy in miles per gallon. Let's temporarily remove the data points from the graph and just look at the graph of the equation. So our goal is to find where the fuel economy is largest and smallest. The largest value will occur somewhere around here when the graph hits a peak. This happens when f of s stops increasing and starts decreasing. And in calculus terms, this is when f prime of s switches from positive values to negative values. To figure out where this happens, let's compute the formula for the derivative function. F of s is a polynomial function, so we can use the power rule here to get f prime of s equals 0.0006 s squared minus 0.0802 s minus 2.2574. And this is measured in miles per gallon per mile per hour. Let's look at a graph of f prime of s. Here is a graph of f prime of s. When the values of f prime of s are positive, this means that each additional mile per hour will increase the fuel economy. And when the values of f prime of s are negative, this means that each additional mile per hour will decrease the fuel economy. And so when we switch from increasing to decreasing fuel economy, this is where we'll find the maximum fuel economy. In this case, this happens when the value of f prime of s is 0. When f prime of s is 0, the value of s is called a critical point. To find the value of this critical point, we would need to set f prime of s equal to 0 and solve for s, either using here the quadratic formula or a computer. We'd get s equals 40.294 miles per hour. So, for cars in 1984, the fuel economy is maximized when traveling at a speed of 40.294 miles per hour. And we can see this on the original graph. Here's the original graph of fuel economy versus speed. And you can see that it hits a maximum value when the speed is 40.294 miles per hour. Now, what about finding the minimum fuel economy? The minimum fuel economy should occur when f of s stops decreasing and starts increasing, or, in calculus terms, when f prime of s switches from negative values to positive values. However, in this scenario, there isn't any speed where the fuel economy stops decreasing and starts increasing. Instead, we can see that the fuel economy is lowest at either the smallest speed value that we're using or the largest speed value that we're using. These are called endpoints of the interval of speed that we're looking at. To determine which of these speed values gives us the smallest fuel economy, we can either look back at the data in our table or use the formula to compute the fuel economy values at each of these speeds. For 15 miles an hour, our formula gives us 21.1 miles per gallon, and at 75 miles per hour, our formula gives us 20 miles per gallon. Thus, we'll have a minimum fuel economy when we're driving at 75 miles per hour. So, to summarize all of our work here, optimization is when you want to find maximum and minimum values of a function. The maximum value will occur when the values of the derivative go from positive to negative, and you might also need to check the endpoints of the domain. Similarly, the minimum value will occur when the values of the derivative go from negative to positive, and again, you might also need to check the endpoints of the domain. The places where the derivative switches between negative and positive values are examples of critical points. These are places where the value of the derivative is zero, as in the example we saw here, or potentially where the value of the derivative is undefined. So, to find all of the potential points where a function has a maximum or minimum value, you would identify all of the critical points and also look at the endpoints, and then see which of these are maximum values and which are minimum values.